Miranda, pronounced right. And he's going to talk about a bird's eye view of dynamical mean field theory inspired approaches.
Okay. I decided that I would take, although this was advertised as a research talk, I decided to take a more light approach to the problem. And I decided to sort of walk you through the very many DMFT and DMFT-like approaches to strongly correlated systems. So I hope this will be less of a technical talk and more of a general talk with a broad view of the subject. So let me start by acknowledging my collaborators over the years that have worked with me on these approaches. So first of all, Vlado Rasavljević, a good friend from the US with whom I have collaborated for many times. My students, Daniel Garcia, postdoc, who is here actually, Maria Carolina Guiar, a former PhD student, and Castro Andrade, who is also okay. Also, Darko Tanaskovic, who was a student of Vlad's, Karen Hauberg, and Marcelo Rosenberg from Argentina, Gabi Cottier, and Edihu Abraham. The outline of my talk is basically what I showed there. I will first talk about the original DMFT approach, focusing mainly on the physical idea. I will show some of its achievements over the years. And I will then discuss a little bit of the current challenges of applying this method to strongly correlated systems. Then I will talk about what I call extensions of the original method, in the sense that they are inspired by the original idea of the dynamical mean field theory, but they actually go beyond it. So I'll talk about so-called StatDMFT theory for distorted systems, cluster-like extensions, and EDMFT, or extended dynamical mean field theory. And then I'll conclude. Okay, please interrupt me if you have any questions. So, as usual, since I'm going to talk about mean field theory, I will start by explaining in very few words the basic idea of the usual Weiss mean field theory of magnetism that probably everybody here is familiar with. So if you take the Heisenberg model in a lattice, like this, say in 2D lattice, everybody knows that this is a very tough problem to solve. Actually, an analytic solution can only be found in 1D, and still, even in 1D, it's a very complicated problem. So, the Weiss mean field theory for this system starts by focusing on a particular lattice of a particular site of your lattice, let's say site I, and then to realize that this spin at site I is in contact through an exchange interaction with Z nearest neighbors, which I showed here. So if I just want to look at the dynamics of the spin Si, it will only suffer the influence of its Z neighbors. Now, of course, the Z neighbors there the sum over the Z neighbors can assume many different configurations. So the idea of the Weiss mean field theory is to substitute this complicated fluctuating quantity by its average. Now, you might ask, average with respect to what? Calculated with respect to what action or to what Hamiltonian? I'll come back to that later. But just imagine that I can substitute this by its average, and I'll call it B. And this is the so-called Weiss effective magnetic field. Then if I do that, that spin that I had on site I will be under the influence of this single fixed magnetic field B, and this is a very easy problem to solve. So it's a spin in the magnetic field. Everybody has done that at some point, right? So for instance, here I show the partition function of one spin subjected to a magnetic field along the z direction. Okay? And just sum over the values of the spin along a certain quantization axis. Now what you do is you come back to your problem, and then you specify how you calculate that average I talked about. So the field B, as I said, is the average over something of this quantity here. And now I know how to calculate this average. So I imagine that I have a sum over the neighbors. They're all equal. So this is nothing but z times the expectation value, or the average of one of the spins. And now I can calculate that expectation value with the Hamiltonian that I had before. Okay? So this expectation value is easily calculated again. It's given by this expression. And this is then equal to B, the field I started with. So if you look at this expression, you can write it out in terms of really one function and so on, but it doesn't matter. You have here the B field, which is something I don't know yet what it is. It appears on the left-hand side and on the right-hand side. So this is actually a self-consistent equation for the B field. Okay, so if you solve that nonlinear complicated equation, actually it's not so complicated, you can find the value of this Weiss field B. The important physical content here is that each spin on your lattice sees the average magnetization of its z neighbors. Okay, so if you do calculate the value of z that comes out of this equation here, at zero temperature it's a finite value, and then as you raise the temperature it goes down, and it goes to zero at a certain critical temperature, which in this case is given by z times j. Okay, so for T greater than the critical temperature, B is 0. Okay, it's a paramagnetic state. Actually, in this case, the mean field theory is not very useful. And for T less than Tc, the value of B is different. And this is just the magnetization of your system. It's a ferromagnetic system. I forgot to mention over there. I'm assuming a ferromagnetic exchange coupling constant. So this is the essence of the magnetic Weiss mean field theory. So let me highlight a few things here. That quantity that I substituted the average for, actually the fluctuations of this quantity decrease as you increase the number of neighbors. In other words, if you increase the dimensionality of the system, you have a sum over a large number of quantities. And everybody knows it from the central limit theorem. The fluctuations of the sum of a large number of fluctuating constants tends to be a small quantity. So for instance, the fluctuations of, I said M here, but it might as well have been B, divided by the average value actually decreases as 1 over the square root of Z, or if you want, the square root of D, the dimensionality. So the theory actually becomes exact in higher dimensions. It becomes better and better as you increase the dimension of your system. Of course, you have to be a little bit careful because Tc is given by Z times J. If you increase Z, Tc becomes unbounded. So what you actually do is you rescale J, you write it as J prime or J tilde divided by Z, such that you keep a finite Tc as you take the large dimensionality limit. Okay, so these are the elements I want you to remember when I discuss now the dynamical mean field theory. So if there are any questions at this point, perhaps it's a good point to ask them. Yes?
Is an Euclidean dimension, or is
yes, just the spatial dimensions of the system. Okay. So let's get to the problem of interest here. I'm interested in treating the problem of interacting quantum particles in a lattice. Okay? So first of all, I'll be working on the lattice, and I have a quantum mechanical problem, let's say fermions on the lattice. So in this case, it's nice just to illustrate ideas, to use the celebrated Hubbard model to discuss how to implement this dynamical mean field theory in this case. So here's the Hamiltonian of the Hubbard model. You have a hopping term, okay, kinetic energy of the electrons hopping around in your lattice. And you have a local U interaction between upspin electrons and downspin electrons. So pictorially, you have these guys in spin hopping around the lattice, And if they happen to occupy the same site, then you have to pay extra energy, U, meaning there is a strong Coulomb repulsion when they are on the same site. Okay? This is the simplest correlated model that you can write for quantum particles in a lattice. So the dynamical mean field theory starts by sort of following the same path that we had before, except that now I have a quantum problem. Okay, so what I try to do is to focus on a certain lattice, certain lattice site, and I try to look at the dynamics of the site under the influence of its neighbors. Okay, so the term in the Hamiltonian that does that is the hopping term. But then first, if you want to follow the analogy further, you realize that you cannot simply take the average value of the creation operator. This doesn't exist. Okay? But you have to do a little bit better than that. So the first thing to realize is that if you focus on a single site in the lattice, this hopping term does not conserve the number of particles in that lattice site. Okay? So if you follow the timeline of a particular site, okay, this site here in the lattice, and you look at it a long time, what's going to happen is that sometimes it's going to be vacant, sometimes it's going to be singly occupied, with an upspin electron, downspin, doubly occupied, singly occupied, vacant, and so on. Okay? So it has a certain history a long time, and this history is what is necessary to follow if you want to define a mean field theory for this problem here. So just from this particular example here, you already realize that the mean field theory in this case is not going to be as simple as in the magnetic case. Okay? So remember that this means that an electron can leave the site, wander off the lattice, perhaps even come back. Okay? And he can keep on doing that. Okay? I will often call the rest of the lattice as the bath. Okay? The bath that to which this particular site is subjected. So what you can do is you can define a timeline function, a function of time that follows the dynamics of the particular site. And this function is this calligraphic G0 here. Okay? So this is a function that's going to tell you how the history of that particular site evolves through time. So at this point, I introduce a particular function here. This is a number. It's actually a C-valued function. So it's actually an infinite number of real values or complex values. And the other thing that you need to realize is that since now the electron can be destroyed at a point in time tau prime and created at a later time tau, this will require, this is a non-local term in time, in the time dimension. And this will require a sort of an action description rather than a Hamiltonian description, which we talked about in the morning. Please.
What's the connection of this S0 to the one you would normally write down for the original Harvard model?
I'll come to that in this and next slide, I think. And if you're not satisfied, then you can ask me again. Okay. So the first thing I do then is to encode the timeline of the electron on site I inside this action term here. Of course, if you put back the interaction term, which is local, so the electron on that side will be subjected to the local U term, you get a full action for the single site that you picked out from your lattice. Okay? So once again, I emphasize that G0, calligraphic G0, plays the role of the device field here. Instead of a simple number, it's a full function, so it's a much more complicated calculation now. And it should determine itself consistently. And the question now is how. Okay. So the way we do that is the following. I have this action here. So this is a one-side quantum interacting problem. So what I have to do is to solve that problem. I'll have plenty more to talk about how to solve that problem later. But at this point, just imagine that you can do that. And solving that problem means you can calculate this so-called Green's function, local Green's function for that particular site. Okay, somehow. And once you calculate that Green's function, you can calculate the self-energy from its definition. So Dyson equation. Yeah?
Question. I know it's much easier to work in imaginary time here. Is there any technical problem working in real time with instead of 1G, you're going to have retarded bands?
Sure. You should, of course, yeah, no problem.
But to actually push the program, is it possible?
Well, it depends on, as I'll emphasize later, this is the hard part of the problem, how to solve this. And the question of if you can solve it in imaginary time or real time depends on the technique you use. And I'll talk about that later. For instance, a very common method is quantum Monte Carlo. Quantum Monte Carlo, you have to do it in imaginary time. It's very hard to get real-time quantities from quantum Monte Carlo. That's a big problem with that particular method. But if you employ another method, perhaps you can work in real time. Okay, so this will be a major part of what I will focus on later on. Okay, there was another question. Yeah.
Can I think of the previous action that you wrote down as just an effective action got out of integrating on all the other steps?
Yes. Yeah, there's a little bit of a twist there, but yes. Let me finish the next sentence, then I'll come back to your question. But definitely, yes, you can. Okay? So, the self-consistency now is imposed by realizing the following. The path that this particular site sees is composed of other sites. And in this particular case here, this is a translation invariant problem, so all the other sites are equivalent. So the path, the rest of the lattice, is built from sites which are identical to the site you picked. Okay? So that means that physically, it has to be that the local lattice Green's function, in other words, if you take the full lattice Green's function and calculate it in a particular site, so I call it GII, in Fourier space, this is just a sum over k of the lattice Green's function, and it has to be equal to the Green's function you calculate for the particular action I have. So you see here, in this particular, so this last part of the equality here, you have on the left-hand side a sum over k. Here you have the dispersion of the lattice. Here you have the self-energy that you calculated when you solved the impurity problem. And this has to be equal to G. Okay, so the lattice information comes through this equation. Okay, up to this point here, you only have a local problem. The lattice information is contained in this next equation here. Yes?
Self-energy is function only of formula.
Next sentence. Next sentence. So in the above, it was implicitly assumed that the self-energy is local. In other words, it doesn't depend on K. Okay? So, in principle, a self-energy is, for translation, invariant system is a function of K and omega. But there, I sort of cheated a little bit and I omitted any K in it. Okay? So it's a local self-energy. Okay, so at this point, this is just a recipe. Okay? I'm just listing the steps in a particular recipe that you have to follow to calculate in this particular system. But this full procedure can be shown to be exact if you take the appropriate infinite dimensionality limit. So this is not just a recipe that I took out of my head. This is a recipe that can be proven to be exact in the large dimension limit, just like the magnetic Weiss field theory that I talked about. So, just as in that case, you have to rescale quantities in the appropriate way, and in this case, we have to rescale the Hopf by 1 over the square root of the number of neighbors. Now, I have many questions here, so let me take this one here first. Okay.
Usually, Weiss field theory, you have to decouple according to different order parameters.
Mm-hmm.
Here, so far, okay, maybe it's just to give the example, but you use CC or particle hole
Right.
channel. But for example, if you wanted to study superconductivity, you need to have other.
Sure,
so you
sure.
have to have other decoupling.
Yes, of course. If you have, for instance, if you're interested in a local, from the full explanation, you realize that you're taking into account correlations on a local approach, in a local way. So if you have a locally driven superconducting state, yes, absolutely, you should generalize this to a full, anomalous Green's function and so on.
And does it work in the attractive Hooker?
Yes, you will have that. There was another one over there.
So the exactness in the limit of infinite dimension is one thing, but the other thing is whether there is a variational lower bound to some kind of free energy that exists in the midfield case.
Some kind of?
I mean, a lower bound to the free energy. So do you know, I mean, in the midfield theory is a good theory because you always know that whatever you find will be always above the ground state energy. If it's the midfield theory.
Well, but that's true of any theory.
Is there a variational?
Well, there is a, you can define this procedure through a variational procedure. You can't do that. I unfortunately did not cover it here, but Gabi Kotlier and collaborators have done that. You can actually define it as a variational procedure. So you can, for instance, you can write it in a way that this G0 is a variational parameter. You know, but you can get by minimizing an action. I don't know if that's what you're asking, but that can be done. You can actually look at it as a Landau theory also.
It's not minimizing, it's extremizing.
Or if it's a complex number, yes.
It's unfortunately not an absolute minimum. It's a sample.
Yes, yes. Okay. So let me perhaps point out to you that the first work that actually considered this particular large dimensionality limit, the work by Lester and Faulhard. There are other important works of that time, and I should point out to you, for people who are interested in going into more detail, these two by now old reviews of this subject. Okay. All right. Any other questions at this point? Okay, so just recapping the algorithm here. Okay, if you start with an initial guess for your sort of order parameter G0, calligraphic G0, you can define that local action I wrote. You can solve it and find the self-energy and the Green's function, and then you can impose self-consistency. So this is the same equation I had here. Okay, just written here again, and now in terms of G0. Okay.
So in the last slide, the G lattice has the same script.
Now, so what I did there is I just substituted G0 from this equation into that equation. Okay? So then you have this equation. Okay? By doing it this way, you can see that if you get from step 2 the sigma function, the self-energy, this will give you a next iteration value for G0. Then you can iterate the loop. Okay? Now, I guess at some point somebody asked me if I can look at G0 as the Green's function. I don't remember what the question was, but yes, G0 can be shown to be equal to, well, omega minus the hopping element times the Green's function for getting out of the site I, wandering through the lattice without ever coming back to that site, except at a later time t prime you come back. Okay, so let me say that again because it was very confusing. So you can show that this G0 here can be given by, well, omega minus t times going out of the lattice, wandering off the lattice, and then coming back again. Okay, t squared. Okay, so there is an interpretation. The only thing you have to be careful about here is that when you go out of this site, you should exclude the possibility of coming back to it except at the final time of your excursion. Okay, that's just a small technical detail, but that's basically.
Still confused about
okay.
The relation. They start with the Hubbard model,
Mm-hmm.
and you ask me what action do you write down. The U term is certainly what I write for the interaction.
Mm-hmm.
Can then determine this is C dagger d by d tau to C minus the.
So
I mean, yeah, that's it.
So maybe if I can write it here. What I'm saying is that I can write the T0. I don't know if you can. T0 term, you can write it as omega minus t squared times the full lattice Green's function here. Okay, let's see. If you go out to a certain site, let's call it J. And then you come back from K. It's J, K of omega is the lattice Green's function. Now, except that I'm going to put here the small thing here. Okay, because, okay, these are processes where I hop out, wander off, come back again through another different neighboring site K. Now, this small I here means that this lattice Green's function is calculated by plucking out that particular site I there. That's the only little detail, but that's basically what it is. So you can actually interpret this Rice field in this way, and it's actually useful. I didn't emphasize it, but it's important. So I stress again that the hard part of the problem is to solve this impurity problem. Okay, this is basically what's called a single impurity Anderson problem, or an Anderson model, and it's a fairly complicated correlated problem to solve. So what one needs to apply this procedure is a good, efficient, flexible impurity solver, and that's not very hard; it's very easy to find. Okay, I'll come back to more details about that later. So let me talk about now some achievements of this approach. So first I will talk perhaps the first achievement that can be ascribed to this procedure is the mod transition that we heard so much about in the last talk. So the mod transition in this case means that if you, for instance, if you have one electron per lattice site, then if the electron wants to hop to a neighboring site, it can do so only by paying extra energy U. So it's a problem. It's a process that's suppressed in energy because of this extra pay in energy. So in effect, what you have is that for U smaller than a critical value, your electrons will be able to do that. Okay, they will pay an extra energy, but they will be able to delocalize, and you have essentially a strongly correlated method. But if you increase U up to a certain critical value UC and above that, what happens is you create a hard charge gap in your system. And at low energies, electrons cannot hop to the neighboring site. So you effectively have an insulator, a so-called locked insulator. So in this case, if you have n equals 1 electron per site, there's a metal insulator transition as a function of U. Okay? And this transition, as we heard before, is believed to take place in several transition metal oxides. There are some examples there. Here we heard a lot about this compound in the last talk, and also V2O3. Okay, and the idea is that in real systems you can tune this ratio that controls the transition by pressure or chemical pressure and so on, as we also heard about in the last talk. So people apply this procedure that I just described to this problem, the problem of the Hubbard model at half filling, and the picture that emerged is such that first of all there's this phase diagram here, which is very similar to the phase diagram that you see in real systems. In particular, you have this first order line ending at the critical point here. Since this is the first order line, there is a region of coexistence of two phases. You have a Fermi-Libet phase at small u, an insulator at large u, and at lower values of temperature, you have other possible phases, perhaps an antiferromagnetic phase, that will depend, the full richness of the low temperature phases will depend on details of your problem. But apparently this structure that I wrote here with the first order line ending at a second order critical point is robust to these low temperature details. So the picture, this picture can be best illustrated if you look at the local density of states of the system as a function of U. So this is obtained. I will talk about a little bit more about the method that was used to obtain this, but at this moment, just imagine that the impurity problem was solved in some way, and then you get the local density of states. So you see for small interactions, you have basically the density of states of a metal. You have a finite density of states at the Fermi level. As you increase U, you start to develop some features here. So you have the low energy, the lower Hubbard band, the upper Hubbard band, and here in the middle, for U less than U critical, you have quasi-particles. Okay, you have mobile particles, and you have a strongly correlated metal. And then at large enough U, all you are left with are the upper and lower Hubbard bands. Okay.
The payload plus particle is almost the same?
Yes. It can be shown to be pinned to this non-interacting value. This is actually exact same. Okay. Yes?
can you say anything about the slope of partial referential map?
I don't know. Why? I mean, the slope.
Yeah, slope. So, you know,
If it's this way or that way.
Yeah.
Well, this is the phase that comes out of the calculation. I don't know if it can be changed by changing parameters of your microscopic model. I don't know. This is what was obtained for the Hubble model.
Isn't it dependent on the particle hole asymmetry of the starting model?
I suppose.
If
Well,
it's symmetric, it will go straight up.
yeah, probably. Yeah. I guess. Yeah.
Yeah.
Yes, of course. So the nice. Oh, there was another question here.
What's W?
W.
U over W. Oh, is it bandwidth?
Where is it?
It's the normalization.
Oh, it is bandwidth. Yeah, bandwidth. It's T. Yeah. So the nice thing about this approach is that it unified two different pictures of the Mott transition that existed at the time. The so-called Brinkman-Rice picture that describes the quasi-particle disappearance of the quasi-particle peak, and the Hubbard tree approach to the Hubbard model, which is able to describe the two bands. So this was the first time in which these two features were seen in the same unified approach. Yes.
Can you comment a little bit on the I guess the Brinkman-Rice approach? So we get a quasi, say at U equal to 3 or 2.5. So we get a quasi-particle peak at omega equal to 0, and then there is almost nothing, and then there's two bands probably developing.
Yes, there was a little bit of discussion whether this is actually empty or if it's just a low weight region. This is very hard to determine.
No, the other question is why do I have a low energy quasi-particle and then nothing else in this picture? I have a quasi-particle at omega equal to 0. In principle, I don't.
Yeah, as I said, it's not clear that the spectral. You can actually see even in this picture, it's not clear that the spectral weight here is 0. Okay, there might be incoherent excitations in that region. Okay, so once again, this is the more detailed phase diagram for B203, where you can actually see the coexistence region here across the first order line. So, okay, so much for the Mott transition. If there are any other questions about the Mott transition, I'd like you to ask them now, but if not, let me move on. Let me talk a little bit about disordered systems. You might ask yourself, okay, why don't you apply this scheme to a disordered system? And of course, the answer is yes, you can do that. And the first thing, okay, so in principle, this is a method that can be applied to both correlated and disordered systems, and it has been applied. Let me mention here very briefly, I'll come back to it a little bit later, that disorder is actually here treated on at this so-called CPA level. Okay, there's an approximation to disordered fermionic systems, disordered systems in general, which is called CPA, coherent potential approximation. And you can show that actually if you just apply dynamical mean field theory with this sorted problem without interactions, just get back CPA. And it's well known that CPA does not have Anderson localization transition. Okay, so the sorted treatment of the dynamical mean field theory is incapable of approaching the problem of the Anderson localization transition. Okay. I'll have a little bit more to say about this later. But anyway, you can apply this method. For instance, you can apply it to the disordered lattice, Anderson lattice model. So now I'm generalizing the approach to from a Hubbard to an Anderson lattice model, where you can imagine that there is some randomness in the system. So, for instance, you have diagonal randomness on the C sites, on the F sites, or in the hybridization matrix element, or whatever you want. You can imagine that these are random variables, okay, distributed according to some functions. So once again, again, you can apply the same picture, except that now here you have two bands, a C band and an F band, which are connected by this hybridization V. And then the C electron is the one that actually can hop around. So the C electron will be able to hop to the lattice bath and come back again within this scheme that I showed you before. So once again, the lattice bath here is fixed. It's an average value that you can calculate self-consistently, but once you do that, it's fixed. It's there forever. Now, but mind you that now you have to solve the impurity problem under the influence of that bath. So although the bath is unique, there's only one bath, which is the self-consistent bath. The parameters of the impurity problem are not unique, because the site energy fluctuates, the hybridization fluctuates, and the F site energy fluctuates, in principle at least. So actually you have to calculate an ensemble of impurity problems. So it's a much tougher problem. You have an ensemble of, if one problem was already hard, can you imagine now an ensemble of them? Okay. So applying this method to disordered systems means that you not only have to solve one, but actually a large number of impurity problems. So let me just give you sort of the picture that comes out of this approach, and remind you that I won't have the time to go into the physics of the impurity problem that you define here. But I remind you that this is basically, as I said, an Anderson impurity problem. Okay, and the Anderson impurity problem has a low energy scale called the Kondo temperature, TK, which will govern the physics at low temperature. Now, since the parameters of the impurity problem are random, you're going to have actually a random distribution of Kondo temperatures. Okay, so even within the scheme, you are able to generate a random distribution of Kondo temperatures. So let me show you what the application of this particular theory gave for a class of disordered heavy fermion systems. So these uranium, copper, palladium systems. This is actually the distribution of Kondo temperature that was determined by fitting the susceptibility to this, by finding what distribution gave a good fitting to the susceptibility, and it gives this result here. And so I should emphasize here that if you follow this curve here, this is a semi-log plot. This actually entails a logarithmic divergence for the magnetic susceptibility, which is the so-called non-Fermi liquid behavior, very singular behavior for the susceptibility. So let me try to explain to you why you have this complicated singular behavior in this case. So the distribution of Kondo temperature is given here. Okay? So imagine that you're calculating the susceptibility at a certain temperature T. You have an ensemble of impurities in your system. Okay? Each lattice site is a different impurity. Now, for a fixed temperature T, since the distribution is very large, there will be sites whose Kondo temperature is much smaller than T, and sites whose Kondo temperature is much bigger than T. Now, if you know the physics of the Kondo problem, you know that the response, the magnetic response of a system in these two extremes is very different. In one case, you have 1 over T. In the other case, you have 1 over Tk, a constant given by the particular Kondo temperature. So in effect, what happens is that for very low temperatures T, there will always be spins which are effectively free. I think it's exchanged. It's okay. If the spins which are in this hash region here are spins with a Tk much smaller than T. And these are actually free spins. So they have a response which is a Curie-like response. And it's a very, if T is small enough, can be a very singular response. So what you get after you calculate the full contribution of all the spins is actually a logarithmic divergence, as you can see there. And it can show that the specific heat coefficient is also logarithmically divergent, and the resistivity also has this linear behavior as you go away from zero temperature. Okay, so this is actually results for sort of disorder-driven non-Fermi liquid behavior, which were gotten from this particular approach here. Yeah.
What's T naught?
Well, it's just a scale that comes when you do this averaging here. Okay. Of course, I mean, if you change this a little bit, if you change the constant there. Okay, this is a divergence. Usually you have a constant here. It's next order term. that can be changed if you change that scale.
I'm sorry, how do you compute the resistivity?
Okay, there is I'm not going to go into much detail about that, but there's a particular scheme for calculating a conductivity within this approach. Let me mention to you that basically you calculate conductivity from the current correlation function without vertex corrections. So vertex corrections are actually 0 in this large D limit.
So how do you do different sides? And do you assume homogeneity?
No. It's not homogeneous disorder. This is not, I'm not reducing the lattice problem to one side. Okay? This is still an itinerant, or can be an itinerant system. Okay? So you can actually hop in the system. You have a lattice means function, for instance, for propagating around the system. So you can use that lattice means function to calculate the current correlation function. And all I'm telling you is the simplification that comes in here, that there are no vertex corrections. So it's a simple calculation. Okay?
So in principle you are computing the power loads close to critical limits.
Well, yes.
Last distance gradient.
Yes, you can. This is a lattice problem. You can calculate anything. It's just the approach that is such that it only treats correlations locally. Okay. Now, I'm not sure that this approach will give you meaningful physics for critical behavior. Okay. I think it's actually going to be a trivial critical behavior from this approach because it focuses on local processes. Okay. I'll have a little bit more to talk about if I have time to talk about that towards the end. Okay. When I talk about extensions, this simple approach, I think it's too poor. Okay, yeah. So let me talk a little bit about current challenges in this. As I said before, the hard part from the beginning until now is the impurity problem. It's how to solve the impurity problem. So I just listed here many different methods that can be used to solve the impurity problem, and each has its pros and its cons. Okay, so for instance, coming back to your question, quantum Monte Carlo, you can do finite T, but you can't do real frequencies reliably, for instance. We can do that in perturbation theory. Then there's exact diagonalization, Wilson's RG, density matrix renormalization group. And just to show you how, I'm not going to go through the list here, how the methods have evolved through time. This is an early calculation of the local density of states as a function of U, the same plot that I showed before with quantum Monte Carlo. So there is actually a procedure for going to the real axis, but it's just not very reliable. It's called so-called maximum entropy methods. So that plot is the one that I showed before. This was obtained from perturbation theory. Okay. So it actually misses UC by quite a bit. It's not quite correct. Let's see. So this. Let's see here. This is the MRG, okay, solving the impurity problem compared with the dashed line, which is perturbation theory. Okay, you see some wiggles there that comes from a finite size effect. So essentially, what you do here is you treat that lattice means function here with a finite number of poles. So you have peaks beside the density states like that. Here is the numerical RG, Wilson's RG. Okay, and a comparison between NRG, numerical RG, and perturbation theory. Okay. And here, I think this is probably state of the art today. This is actually density matrix renormalization group applied to this problem. And you can see actually this is in the coexistence region. So this is the metallic solution, and the dashed line is the insulating solution in the coexistence region. So it has very large precision here. You can even identify a certain structure in the Hubble bands there. Let me refer you to a poster by my postdoc later this week on the density-driven transition for this system using this method.
Excuse me, sorry. What side was lower is this?
Excuse me? Okay. You remember I said that it's a first-order line separating metal from insulator.
Yes.
So So there's actually a finite region where metallic and insulated solutions coexist. Of course, one of them is lower in energy, but they actually coexist. The other one is metastable in that region. So this is the plot of the local density of states for those two solutions in that coexistence region. Okay, so you see, U is not varying that much. Okay. All right. Other challenges facing this approach today. So we also heard from Edith's talk that the orbital degrees of freedom in transition metal oxides are important. Usually you have, let's say, a D level, which has a five-fold degeneracy, which is lifted partially by crystal fields and cubic environment, but not completely. So you're left with some leftover degeneracy in the problem, and it's important to take that into account. So those are the important details that the original approach left out that you have to put back in if you want to have a more realistic description. So this is a general two-orbital interacting model, which I wrote here in gory detail. So you have many parameters here. I wrote here U and J and exchange coupling, and so on. So the application of this method to this multi-orbital system actually led to an interesting thing called the orbital selective Mott transition, which is the following. Let's suppose you have a two-fold orbital forming two bands. Okay? Now, depending on the hopping elements, perhaps the two bands don't have the same bandwidth. Okay? So you might imagine that they can be driven, insulated by increasing U at different points in the phase diagram because they have different bandwidths. They might have different critical values of U for going insulating. And that's actually what happens. You have this, for instance, you have this phase 1 down here, where both are metallic for small U. Then this phase 3 inside here, where one band, let's see, phase 3 is over there. One band is insulating, and the other one is metallic. I guess I exchanged them. I think it's exchanges. So this is the one where one can go insulating while the other stays metallic. And then finally, for a large value of U, they are both insulated. So you can have sort of this two-stage process of Mott transition if you have two different bands. Okay. So there's a lot of work going on now on this multi-orbital models. I'm not going to talk about that now. Another interesting challenge these days, a lot of people are working on this, is to adapt this method to treat realistically strongly correlated systems. So what I mean by that is, you remember that the lattice Green's function had two inputs. One was the dispersion of the lattice, E of k. The other was the self-energy, which contained information about interactions. So basically what you do is you treat the self-energy within DMFT, and you treat the hopping part realistic using one of these well-known band structure methods, let's say LDA, for instance. And so an interesting success of this approach was the correct description of this delta plutonium phase, which the usual LDA is not able to get. And this LDA plus the DMFT method was able to show that this delta phase, which is observed, is actually a stable phase. And here you can have this is a comparison of the phonon spectrum of this system to measured phonon spectrum of plutonium. So there's a lot of effort going on right now on this particular application.
So if I talk about electronic structures in common, how do you get the phonon spectrum? Like, how does the G take it from the...
Well, I guess you calculate just, the usual thing, you calculate these force constants, right? You just do ground state energy calculation for different configurations, and then you Born-Oppenheimer approximation calculate. And then you plot the phonon spectrum. I suppose that's what they do, right? That's what's usually done in these LDA calculations of phonon spectrum.
Okay, so the electronic part, you just put the distortion by hand, and then you calculate the...
Let the electrons relax and adapt to that thing, calculate the ground state energy, then do it again, calculate it again. Then you get the force constants, and then you get the phonon spectrum. Okay, so I don't have much time left, but let me talk about extensions now. So what I'm going to talk about now is sort of staying within this local approach to the physics of strong correlations, but going beyond DMFT. Okay, so that's the idea in the next few view graphs. So let me talk about what is called stat DMFT. So it's an extension of DMFT to distorted systems, which is a little bit more sophisticated than the usual DMFT. So basically, the question is, can a scheme be devised for distorted systems, which is able to treat correlations locally and also Anderson localization? As I said before, usual DMFT has no Anderson localization. Okay, and the reason why it doesn't, which I promise I will talk about a little bit, is because each electron in a certain site will see an average path, which is just the average Green's function of the other, basically this thing here, right? Averaged over this order. So it's the average Green's function of the other, of the lattice, it's the Green's function of the lattice averaged over this order. Now, it's well known since 1958 from Anderson's paper that the average Green's function is not critical in the Anderson transition. So it's not a quantity that suffers anything as it goes through the Anderson localization transition. So it's not a good order parameter for the localization transition. So you have to do better than that. So what you can do is the following. So remember, the DMFT was focused on a particular site and look at the dynamics of that site in the neighborhood of the other sites of the lattice. So I tried to picture here a distorted lattice, so the size of these circles here is supposed to be the value of the on-site energy. So a particular site will see a certain environment here, which is going to be different from the environment that this guy will see, because it's located in a different point of your lattice. So the idea is to define this Weiss field here, G, to be site-dependent now. Okay? So it's going to vary from site to site. So this is a little bit different than before. Before, this was G0 was a fixed value for any site of the lattice, whose physical interpretation, as I said, is the average Green's function of the lattice. But now I allow for GI to fluctuate spatially. So, okay, so I can solve these impurity problems, and then the problem is how to impose self-consistency. But basically what you do is the following. If you imagine that if you keep the assumption that the self-energy is still only a function of omega, but can vary from site to site, okay? Basically what you have to do is to append to the local site energy a correction which is frequency dependent, coming from the self-energy, and then you can solve the lattice problem for that state. Okay, so basically, instead of solving a non-interactive problem with a certain site energy at each site, you just add a self-energy to each site, and then you calculate the Green's function again of this lattice. Okay, so this closes the self-consistency loop, and the difference here with respect to the other approach is now that each site continues to see the rest of the lattice, but what it sees depends on where it is. Okay, so if we go from here to there, it's going to be different. Okay, so this allows for fluctuation, for spatial fluctuation. Okay, and then it's able to get the transition. Sorry.
You said that you constrain the self-energy to be dependent only on the frequency.
That's right, but also very spatially. So there's no K now. No, because K is not a good quantum number now. It's a distorted system. K is not a good quantum. Excuse me? There's no K, right? It's not a translationally invariant system. K is not a good quantum number. Okay? So you have to think locally now. And act locally.
The bit of interaction, one of the risks is that now you have like a glass. You may not be able to find this meaning of the minimization problem.
Yes, absolutely. Yeah. So the interesting thing of this approach, for instance, is if you make U equal to 0, this is an exact approach. The distorted problem is exact. Okay? If you take the dimension to infinity, you get back the DMFT. So you have the right limits there. Okay? In between, it's just an approximation. Because this is neglecting inter-site correlations. This is still local.
So in which sense you constrain the self-energy to have only orbital premises?
Because it comes from solving this problem here, which is still a local problem. Okay?
So now you have to solve the impurity problem at each site now?
Yes.
For iteration?
Yes. This is a very expensive method now. Okay? It's fairly non-trivial to find converged solutions, and sometimes they probably don't. You can't find them. Yes?
How many sites have you put into?
Well, it depends on the, well, ideally you want to put into this number, right? It depends on the impurity solver you use. If the impurity solver is too sophisticated, it takes a long time, then it's impossible to do a large lattice. Okay. So for instance, my student, he can do it with slave bosons. The impurity problem is with slave bosons. He can do up to 50 sites, 60 sites. Okay, so one of the applications of this method to, once again, a distorted Anderson model was made, and you remember we had a distribution of condor temperatures before, and it was actually fitted to the experiments, but now we can actually calculate what those distributions are. And one of the nice things we get is we get a power law distribution of condor temperatures with an exponent alpha, which varies with disorder. And if alpha becomes smaller than 1, then this is a divergent quantity. It's a singular distribution, and it gives rise to divergence in the thermodynamic responses of the system. Okay. So once again, I call your attention to a poster session tomorrow on the application of this approach to the 2D disordered Hubbard model. Okay. Other extensions are, for instance, so-called cluster DMFT, where you, instead of focusing on one lattice site, okay, you now incorporate a little bit of non-local correlations, but not too much. Okay, so quasi-local correlation. So if you instead of focusing on one lattice site, you can focus on a plaquette. Okay, so then you try to solve the problem of a plaquette of 4 sites embedded in a bath, in a bigger bath. Okay, so you try to do as best as you can in this 4 impurity problem here, which is formed by 4 sites embedded in a system of other sites. Okay, so now of course the Green's functions, the Weiss field, the self-free energies are actually matrices with indices that run through 1 to 4 in this particular case I showed you. Okay, so the motivation here is to incorporate a little bit of non-local physics, but of course long wavelength physics is still outside the range, the scope of this approach. Okay, so it's quasi a local physics that you're incorporating here. There's also a scheme, so this is a sort of a real space scheme. There's a scheme in K-space, which is called dynamical cluster approximation, but I won't go into all these details. So one particular application of this method to the Hubbard model was made by these people, and here is a color contour plot of the spectral function A, the imaginary part of the Green's function. And one of the nice things that comes out is a K-dependent spectral function in the Brillouin zone with cold spots and hot spots for the Hubbard model, which is sort of a topic that has been much discussed in high GC cuprates. Okay.
That's 2-dimensional, 3-dimensional?
It's 2-dimensional, so 2-dimensional Hubbard model. Okay. There's a recent application of this cluster DMFT to the Condor lattice or periodic Anderson model, and an interesting result of this approach is the observation of the so-called Dynamic phase transition, quantum phase transition, where the ferromagnetism dies to 0, and then you have a paramagnetic phase with a quantum critical point here. We're going to hear a lot about this during the rest of the week. Okay, so this is a particular application, cluster DMFT to this method. Finally, the last extension I'll talk about, I don't know, there was some question before that's related to this, is this so-called extended DMFT, which was pioneered by these people. And the idea here is the following. Okay, you still take a local approach to the problem, but now instead of treating one-site processes in the mean field, like we did, okay, taking the Green's function as your sort of order parameter, so what I said, the timeline function for the electron. Here you consider the same approach as applied to a term that has a 4-fermion interaction. Okay, so let's say a spin-spin interaction like this, which is equivalent to 4 fermions, like that. Okay. So the idea now is the following. Okay, so this guy will see the neighboring site through this interaction with that guy. I think it should be J over there as well. Okay, it should be J. And the recipe is the same as before. So you assume you substitute Si, the interaction Si as J, by a retarded interaction on site. So the same site I, the spin interacts with itself at a later time through a Weiss field or a Weiss function chi 0. Then you can calculate chi for this particular problem here. This is a complicated problem. Basically, it's the Green's function for the spin. You can define once again a self-energy which I call C, a spin self-energy C. And you can impose self-consistency by imposing that the local susceptibility you get from this local action is equal to the lattice susceptibility, to the local lattice susceptibility. In other words, the sum over K over Q of the Q lattice. So it's the same recipe now, except that now I'm treating 4-fermion interaction terms. Okay. So this approach has been applied by Chimiao C and collaborators to this problem of quantum criticality, and they came up with this concept of a local quantum critical system, in the sense that not only, as we are used to, long wavelength modes are important at the phase transition or the quantum phase transition, but also localized modes are critical. Okay? They suffer a critical transition as well as the extended modes. Okay? So in a sense, this is a scheme for a new universality class for quantum phase transitions. As I said, the localized modes are as important as long wavelength ones at criticality. But the only snag with this theory is that for it to be non-trivial, it requires 2 dimensions. Okay? So if you apply this in 3 dimensions, you have conventional critical behavior. So only in 2 dimensions do you get, for instance, this divergent local susceptibility or a lattice susceptibility with omega over T scaling and so on. Things which people can actually fit experimental data to this particular form here, as I'm sure we'll hear about towards the end of this week. Okay. So this is a scheme where now, yes, the local modes, they have non-trivial critical physics. Okay? Whether it applies to real systems is a big question mark. Okay? I think the jury's still out. It requires 2 dimensions. So in 3 dimensions it doesn't work. Okay? Yes. Okay. I think I was right on time. So just to conclude, as we wrap this up, I talked a lot about DMFT, and I emphasize this is an arena where you can treat strong correlation effects on a local footing. Okay, and it's a systematic scheme for doing that. Okay? You can do it in a very precise way. It has some successes, and I would say perhaps some first steps towards successes. And I showed, for instance, the picture of the Mott transition, delta plutonium, hotspot, Griffith's phase, Dynamic transition. But of course, I think many challenges still remain, and particularly in the extensions and that I talked about. So thank you.
Questions?
I just wanted to understand the distribution of coefficients, because you have single lattice and unit.
That's right.
And then you introduce some anisotropy, so that, as far as I understand, that at the end of the day, you have effectively some spin 1/2 quantum unity with several anti-parametric problems.
No. Okay, if you want to think in terms of condor lattice, you can think of many condor impurities, each with its own coupling constant J.
Okay.
Each has its own J, and therefore...
You should treat them separately.
Yes.
Okay.
And at the end, of course, you have to impose self-consistency of all of them. But once you find the self-consistent bath, in that bath, you just have to calculate the many TKs for each J.
Any more questions?
In your sort of cluster calculation,
Not mine.
did you see any qualitative difference in metal interest punch?
Well, yes, there are. You're asking, I guess, if the picture that emerges from the cluster DMFT is the same as the usual DMFT. No, it's not. There are some very essential differences there. So for one thing, just let me mention one, for instance. The mass renormalization is a much more non-trivial quantity, because now they have not only frequency dependencies, you also have K dependence. Okay, so for instance, you have the quasi-particle residue Z, and the ratio of effective mass M star to M. In DMFT, these two quantities are the same. Okay, or the inverse of that. Okay, they are precisely the same, but they all come from frequency dependence. Once you have K dependence, they are no longer the same. Okay, so they become actually separate quantities. Now, the phase diagram, as far as I know, is not changed that much, but details are very different. Okay.
You don't have something like a super
I don't think I've seen that. Perhaps they have something which I haven't seen. I don't know.
I have one.
Let me just mention quickly. There's another paper which I didn't cite here, which has Fermi arcs. Okay, I didn't show those things here. So I don't know. Perhaps they have addressed that question. But they apparently have Fermi arcs.
Clustering field or variational field, as otherwise, is now understood in terms of a cluster expansion of the exact thermodynamic partition function. So in that sense, you increase the clusters, you're reaching a limit, you're just truncating your expansion. Is there a similar interpretation in the DMFT cluster version?
Good question. The other thing is I don't know. I suspect no. Is there?
I would say yes, there is. I mean,
okay, but I don't know.
The notion is that there's a functional of real system which spits out the self-energy if you give it the Green's function. And so you're taking that functional as a function determined by a cluster. So yes, there is. Okay.
Any more questions from the audience? Yes.
So, what's important in cluster DMFT K-dependent hypothesis? Do you find that the effective mass actually does not diverge?
At the transition, it diverges.
Effective mass does not diverge, but
it diverges. Yeah.
It diverges when 3 goes to 0.
Yes. But it's a different dependence.
That's a different dependence.
Yeah. I don't think the critical behavior is different. There's no question.
I have a question of how to put it to the test with some system that we actually can. We either know the exact solution or a model that we can cook up an exact solution. So one example would be, because for example, even superconductivity in an attractive Hubbard U model, well, we know that that's kind of a weak coupling problem, right? Whereas in the positive large U, that's strong coupling, but we don't know the solution. So DMFT is just
you have 1D. They have compared it to 1D. The cluster method, not the original method.
But 1D, you could say, well, maybe 1D is accurate. But so two systems that I could think about. One would be, the quantum Hall effect, where any mean field theory is already complicated. Like for example, composite fermions with H2 flux 2 planes to see a Lofting state 1/3. That would be one example.
But it's not a lattice problem.
Yes, that's why I was hesitating about. But then I would go to the next step, like a bosonic, because this in principle could work for a bosonic model.
Sure.
So you can have bosonic models so that you don't have a sign problem, that you can actually hook up the exact ground state wave function. For example, examples of similar models are quantum dimer models, for example. And then in those models, you know the exact unibody wave function. So then one could do another check that, okay, here's a system that we actually have something to compare with. How good a job do we do in 2 dimensions?
Well, people don't know much about the Bose impurity problem. It's actually a problem that's being worked on right now. I mean, there was a very recent paper on the impurity problem with bosons, for boson. So I think first people have to learn about solving bosonic impurity problems before addressing it. Well, there are already papers out doing that. They have applied it to the superfluid Mach transitions in the bosonic Hilbert model. They didn't apply it. I mean, they solved it with an eye to that application, and it seems to have the right features, but still needs to be.
So you're saying that.
But if you have dimer order, I think you have to go beyond local, and you have to do some cluster thing. Local is certainly not enough for dimer order.
But then the question is, well, if you can only do something local, it's good for gap systems, for example, right? If the system has a gap, then it's okay in that, doing local approximation should work.
Yeah. It certainly doesn't have a lot of other features, so I agree.
But it's okay if, for example, for superconductivity, if you have a large gap, then that's more interesting.
Short correlation length.
So initially you were making a guess of the Z0.
Excuse me, I didn't understand.
So in the impurity problem that you have, in the regular DMFT, you were making a guess for Z0 initially.
That's right.
So didn't ever happen to you specifically, because you're a practitioner of the to find more than one solution with different guesses. So to solve the impurity problem, finally you find different functions.
Well, this actually happens. For instance, let's take the example of the Hilbert model. If you do not assume antiferromagnetism, you get a solution, a Mach insulating paramagnet. Okay. Now, if you have to allow for an antiferromagnetic solution to be able to find it, and it's actually lower energy. Okay, but you have to allow. So the other question by Claudia, if you don't allow for anomalous Green's function, you don't see. So there is a certain. It's not just a method that you apply blindly. You have to do some work.
Okay, so let's thank Eduardo again.
So you know you have to post it tomorrow. The place for the course is already prepared, so you can arrive in the morning. So if you have any questions, if somebody wants to